All right, guys. So here's the warm up. I'm not collecting it. Leave it. It'll be part of your notes. So what's today's date? The 27th, right? 2 days left. February. All right, guys. So here's the question that I want you to think about. So it says, which of the following points is a solution point for all linear equations? So I'm going to give you 3 different equations. X minus y equals 5. 2x plus y equals 1. And then 6x plus 3y equals 3. And then the points that I'm going to give you are 1, negative 3, 10, 5, 2, negative 3, and then 1, negative 1. So which of the following points is a solution point for all of the linear equations? Whatever you think that means. And then see how you would check that. There's 4 points. One of these is a solution for all 3 equations. Which one and how would you check?
I was surprised.
And I think for today, you guys are sitting in a somewhat similar spot to the usual groups that you guys check in with. Let me have you guys check in with your classmates just to do a little double check. Which of those points is a solution point for all the equations? How can you check? Let me prep all this stuff while you're doing that.
That was the rest.
Stressful, man. Stressful. They're gonna do that every episode. That's why I love it.
Yeah, but I remember last year saying this guy.
Oh, yeah, for sure. Yeah. No, for sure. My wife, she kept like walking away. I'm like, no, get over here. Come on. Don't be too scared. Let's do this.
Wait, the last of it?
Yeah.
Oh, I need to start one.
Yeah, you do that. I wanted.
Everyone keeps talking about it and out of bed. So I'm like, all I do is watch K-dramas.
That's all.
You sound like my sister.
I literally love K-dramas.
All right, guys, do a quick check with your groups, just to double check that you guys agree.
And then this one I'm watching right now is just so funny. It's like,
All right, what's the winner? 2, negative 3, correct. How were you guys checking it? What were you doing? Say again?
Plug in the X and Y values.
Plug in the X and Y values, that's correct. So these are the X and Y coordinates. So you plug them in and you just need to see if it satisfies each other, correct? did this one satisfy any of the equation?
I only put.
I like the first one.
Let's see, 1 minus -3, that would give you 4, so that wouldn't work. What about this one here? 2 times 1 minus 3, that wouldn't work. What about this one here? 6 times 1
Minus 9.
plus 3 times -3, also wouldn't work, right? Okay, so remember what I was just saying about the algebraic versus the graphical? 2 weeks ago, you guys learned the shape of this graph. What are the graphs of these going to look like? They're going to be lines, right? They're going to be lines. So the graphs of these 3 equations are lines. When you're plugging in the point into the equation and it does not satisfy the equation, what does that mean graphically?
It's not on the line.
It's not on that point is not on the line. When you plug in the coordinates and it does satisfy the equation, it means the point is on the line. Okay, beautiful. So you guys are telling me that this point is the winner. What does that mean visually? It's going to be a point where all the lines should intersect because it's supposed to be in all 3 of the lines at the same time, right? Well, let's double check. Let's see. So here are the 3 lines. Wait, where are the 3 lines at? Hold on. Oh, actually, I want to talk about that in a little bit. So let's see. There's this line. There's the second line. And then the third line is the same as the second equation. We're going to talk about that in a little bit. Here are the points. And let's see. So notice that 2, -3 is the only one that's on all 3 or that satisfies all 3 equations because it's on the line of all of them, as you guys said. And the one we were checking, 1 -3, didn't satisfy any of the equations, and notice that it doesn't lie on any of the lines. Cool. So this is a perfect example of what I meant between understanding the algebra and the graphical and what they're saying to each other, or what they're telling you actually. Okay. All right, beautiful. So let's practice. Can I have you guys rewrite each equation in slope-intercept form? What is that?
Y equals mx plus b.
Right, perfect. So I want you guys to rewrite each of these equations in slope-intercept form. Let's see what happens.
Isn't that what we did last week?
That's what you did? Yep, that's what we were working on before.
So we have to do over b, c,
Well, in this case, this is a different form. So all you need to do is isolate the y variable.
Okay.
Try to just isolate the y variable. Right, so to get them to this form, all you guys need to do is isolate the y variable. Okay. Let's see this row right here, somewhere in this row, what did you get for the slope intercept of this line? X minus 5. Okay, let's do this row right here. Someone tell me what you get for the second one. -2x plus 1. And then the last row. Someone from the last row, what did you get for this one?
-2x plus 1.
You got also -2x plus 1. Once you divide it by 3 and simplify it. So what's going to happen today, towards the end of, no, towards like the middle of today, is that you'll see 2 equations like this one that look different. But in reality, they're representing the same line. Okay. You guys see this equation in the middle? What number can we multiply this equation on both sides by so that it looks like those third one? You can multiply by 3. So that's something that's gonna happen. If I have an equation of a line and you multiply the equation by a numerical value, it changes the way it looks, but it does not change the graph. It gives you the same line back. Okay? That's a conceptual thing we're gonna use later on. Okay, perfect. All right, so I'm not collecting the warm up, so let's leave it there. And so we're gonna use this, all of this that we've kind of discussed to start our first section here called solving systems of equations. Okay. So consider the linear equations and their graphs. So let's look at two linear equations and their graphs. So we got x minus y is equal to 5, the first one from the warm-up, and then the second one from the warm-up. And so basically, you guys already did a lot of the work, but we can rewrite these equations in slope-intercept form, just the way you guys did right now. And then you got the first one turns into y equals x minus 5, and then the second one gives you y equals negative 2x plus 1. So it's a little, one of the reasons you guys learned this form is because it's easier to graph than if I just gave you this one. Okay. So let me remind you how to do that, in case you forgot. So let's draw our x and y axes here. Go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5. Okay, let's do the first one here. How would you start graphing the first one?
Start at -5 and then
Start at -5 on which axis?
the y.
The y-axis. That's the b value. Remember, the -5 is the y-intercept. So we got -5 here. We plot our point. What's the slope of the line?
1/1.
1/1. So notice the slope here is 1, so the slope, you can think of it as 1/1. So that means from here, you're going to go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. So it'll look something like this. And then the second line, where's the y-intercept for the second line? 1, right there. And then the slope of this guy is -2/1. So what do you do from this point?
Down to
One, -1.
Down 2. Y goes 1, 2 down, and x goes over 1. 1, 2 over 1. Something like that. It's a little crooked, sorry. Okay, and where's the point where they're intersecting? What's the x value? 2, and what's the y value? Negative. That magical point that you guys were just discussing, right? So, when we put all this together, notice that the solution point here, the solution point to -3 that satisfies both equations. Both equations is also the point of intersection. And that's kind of the theme of this section is you're going to do a whole bunch of algebra to answer that question. Where is the point of intersection of two lines? Okay. Questions? Okay. So now we're going to generalize this to like any kind of equations. Okay. Let's see. So we're going to have some definitions. It's going to be 3. So leave some room in your notes for some definitions. I apologize for all the writing we're going to do right now. So if we have 2 or more equations, the 2 or more equations are called a system of equations. That's literally what that means. This chapter or this section is just saying we have more than one equation that we're dealing with at the same time. We have a system of equations. And so we're going to define a solution point for a system of equations must be a solution point for, what do you guys think? So a solution point like this one, this is a solution point for this system. It must be a solution point for all the equations in the system. Correct. Good. But for all equations that are making up the system. And so here's some fancy vocabulary. We're going to say a system with a solution is called a consistent system. A consistent system. So if you guys see the word consistent, that means there's it has a solution point. Has at least one. What does that mean visually? That they have to intersect at a point. Okay. So that means that if there was 2 lines making up, let's just say there's 2 lines, then they have to intersect at that solution point. Okay. Sorry, a little annoying about these arrowheads. Okay. So what do you guys think the other one's going to be called? The opposite. Inconsistent. When what? Or there's no solution. No solution. Which turns out, yes, they're going to have to be parallel. And we'll see why. So a system with no solution is called an inconsistent system. And yes, as Cameron was noting here, if I have a line and I have another equation representing another line, but there's no solution, then they can never cross. So they're going to have to be parallel. So they're going to have to be parallel lines. So what kind of system is this one?
Down.
Consistent system because there exists a solution. Okay. What about these two? These two equations that are really the same equation, the same line.
Would that not even be a system?
Is it consistent or inconsistent?
Contingency if all of them are solutions people.
If it has at least one solution, it's consistent. No solution means there's literally no points out of all the x, y points, none of them will satisfy both. Okay, but in this case, there's all the lines that are on top of each other, all the points that are on top of the line agree on both of them. Okay,
So it counts as a system even if they're the same equation?
it counts in the system. Yeah, it just, they look a little different.
If your problems were written the same, like exactly the same, would that count?
No, because then that really, they are the exact same equation. Yeah. Okay, so what we're gonna do is try to see if a system is consistent or inconsistent, but without graphing. Because it's one method of solving is by graphing, okay? But you see how sloppy my lines are? Okay, we can't rely on our human way of graphing because we might accidentally get a wrong answer. Because a solution point doesn't have to be perfect integer coordinates. They can be decimal coordinates as well. So how do I know this is not really 1.9 comma negative 2.9? Because we did the math, correct. But that's exactly the point, that to get an actual precise solution, we can't rely on just our graphing. We have to actually do it algebraic. Okay. Sometimes you might get a coordinate that's a fraction. And if you guys won't like this, but keep practicing with fractions. Okay, so let's see how we're gonna do this. This part. Okay. All right, so there are going to be two methods for solving systems of equation. One method is called substitution. Maybe that rings a bell to some of you. And the second method is called addition, or sometimes they call it the elimination method. Okay? And so we're going to learn both of them. And then you're going to learn both of them. The homework will ask you to try both of them. But on the exam, I will not force you to pick one. You get to pick whichever one you like, or whichever one is easier to use to solve. Okay. Okay, so let's see. Let's do substitution first. This one's a more familiar one to people. And we're gonna keep using the same system, but then we'll expand and practice completely different. Okay, just so you guys can kind of see the like process behind it, a little bit of the theory behind it. Okay. So let's say we're being asked, this is what the homework will look like. It'll say solve x minus y is equal to 5, and then 2x plus y is equal to 1, and we usually use like this little bracket to kind of name the system. So we're going to solve that system. You already did it graphically, right? And we confirmed it with the warm-up. We already know what the solution is going to be, but let's just pretend we don't know. Just to kind of see the mechanics, and then we'll talk about it. Okay, what you're going to want to do is you're going to pick an equation, and this is where this gets a little scary because it's really up to your choice. You're going to pick an equation, and whichever equation you pick, you're going to isolate one of the variables. You can either isolate the y or you can isolate the x. Okay? So in my notes, I picked the first equation and I isolated the y. So let's do something different here on the board. So let's pick the second equation. Which variable is easier to isolate?
Why?
Y, right? So let's pick the second equation. And let's isolate Y. What do we have to do to get Y by itself? Minus the 2x on both sides. So then we get Y equals negative 2x plus 1. And this bad boy, we're just going to leave it the way it is. Okay. The next step is a conceptual step. What were you guys doing in the warm-up to check to see if the point was a solution point to both equations? You're plugging the same exact x value and the same exact y value, right? You're plugging in the same x as you were plugging in here and the same y that you were plugging in here. Cool? And if it was a solution point, then it agreed on both of them. So the theory is we're looking for the x and the y. We're assuming this y is exactly this y for the solution. It's going to be the same y coordinate. But here's where it's a little funky. We're rewriting this equation to say y equals this expression here. But this y is really the same as that y right there. So then what you're going to do is, since this y equals this expression here, you're going to substitute the negative 2x plus 1 into the other equation's y variable. Okay? And so then when you do that, we're going to rewrite this one as x minus, oh, see how we're substituting a whole expression here? I'm going to put parentheses around. And then literally substitute it in for that y and replace it with negative 2x plus 1. That equals that 5. So it's kind of like you're swapping out this y and replacing it with what the other equation says to be. Okay? And now you're going to be left with an equation with just one variable. Yeah, right.
Isn't that just the same as putting it to an x plus b grid, it's low percent 100, yeah, and it's supposed to be same to each other, like setting equal to each other?
That would be a different way of doing it, correct? Yeah, that's
I'm just saying, because we already had it, so.
correct. But you won't always like,
Yeah, of course.
correct, but yes, that wouldn't be wrong. You did it. Okay, but here's the point, that by doing this, you now have created an equation that only has one variable, which now you guys have the tools to solve. I just got to solve for x here. What do I have to do with, what's my first step that I need to do?
Distributive negative.
Stupid negative, right? Distribute that negative, so then we get x plus 2x minus 1 is equal to 5. You start combining like terms. 3x minus 1. Add the 1 to both sides. You get 3x is equal to 6. And then lastly, what do we do? Write that 3 off. And then we get our first coordinate, which is x is equal to 2, which we know, right? We already know what the solution is supposed to be. But here it's showing us what the coordinate is. Once you found one coordinate, then you just substitute that coordinate back into the equation where you isolated your variable to give you the other coordinate. Okay? So then what you're going to do is you're going to sub x equals 2 into the isolated equation that you found earlier and just replace 2 in there.
Does it matter which equation you use?
It does not matter which equation you use. You can even plug in the 2 into the original ones here. Yeah, you can plug it in here or 2. But since this one's already had the y by itself. So then you go ahead and just figure that out. That's what -4. This one is -3. So what's the answer? The answer has to be a point. Okay, 2, -3. Boom. There's the algebra. Now we know for sure it's 2, -3. It's not 1.9 and -2.9. It's for sure this one. Yeah, which
Isn't it like the g of x that we did last time? Is it like a little bit different?
it has a little bit of the composition stuff in it. Yeah, where you're kind of plugging in an expression into another expression. Yeah, it has that feel to it. Which is why I was saying it's like kind of familiar to you guys because you've been doing that for a long time. Okay, So now I'm gonna give you guys two different systems. And I want you guys to use substitution to find their solution, okay? I'll leave the work up here. All right, so let's try it out. We'll solve these systems. First one is x plus y is equal to 7. And then 4x minus 5y is equal to 10. And then the second system is x minus y is equal to 10. And 7x plus 6y is equal to 5. So remember, you're going to start by choosing an equation and then choosing a variable to isolate. You can isolate the y or you can isolate the x.
Did you, I don't remember, but did you subtract 2x to isolate the y?
Correct. That's exactly right. All right, don't hate me. I am seeing some of you guys getting different answers, and nasty fractions that are coming up. So can I have you guys just check your substitutions real quick? Just check your substitutions. Real quick. This is how we do it, because some of you guys are using the wrong form here.
So did you
Do a quick check.
X from 5 to 8, or did you subtract it from, you added 5 words, or you isolated
Not discussing. I use this.
Yeah.
That's it. I'm gonna stop. I'm trying to isolate Y, right? So but I don't think.
So, well, you have, here's where I was saying you're gonna have choice.
Mhm.
Do I want to isolate the y of this equation, or do I want to isolate the y of this equation? You get to pick. You don't always have to do the second one like I did.
Okay. But if I were to do this one, would I just add X to
Yeah, this point.
side? Oh, subtract.
Yeah.
That's it. See how that's a lot easier?
Yeah.
You probably want to go with that.
Okay. Sounds like. Okay.
Accidentally did the wrong.
Smart on the equation that you choose, make the life less complicated.
So this is canceled out, right? So the equation would just be
Yeah.
7x
X to this side now. So this cancel out or not. Okay.
It is actually.
This one just be 7.
7 minus.
7 minus. Oh, so that would be the equation. Okay.
So if this is review for some of you, please just kind of try to help your classmates out. It might be their first time seeing this. I'm gonna let you guys be the tutors in my case.
And then would I plug that into the Y for X is like 5, would I plug this into this? So,
Yeah, there may be some easier way, but you that should get it in. Yeah, maybe there is.
Oh, God. That looks-
Keep working. I'm just gonna post the solutions. If you want to check. Those are the solutions. Let's see what you got.
Oh, yeah.
You could, yeah, you could. You put that. Minus the one. Okay, good. And you plug it in. The y equals 2. And so what did you do to get that?
I have to, I did this wrong. I suppose that's pretty.
Yeah, maybe number your equations.
I think I actually, yeah, I believe.
I think we're gonna close that. That's a different system. That's you're doing it to this one. This one is this problem.
Oh, sorry, I went to 24.
Oh, that's why. Yes, yeah.
First, I accidentally just wrote this problem, right? I did this, then I was like, oh, I need to do this now.
Yeah. Yeah, be careful. Be careful. Me too.
That's. I know I did something wrong. I know.
So before you start, like, I guess this is fine. You already for see this. These are not like terms. This doesn't have an X.
So I have to do it to this one.
So it would stay. Well, it's fine, but you would just see, because you can combine these. It
Yeah.
would just be 10 plus 4.
For X. Oh, okay.
Okay, you're gonna get 5. Actually got 50. Wait. Well. They got -5.
Could I add it to the 5X?
Instead, if you want, before you do this,
Yeah,
you don't add it. You just combine the terms.
so,
You do 4x minus 5x.
okay, and I'll do 1X. Okay,
Negative 1.
-1.
Don't like it. You plug the -5 into the.
So let me know if you need me to look it over. You still keep getting the wrong one.
Yeah, I just. Oh, no, okay. Sorry. What did you do? I think you're doing.
Taking this part out, and substituting in this one. I said, this is wrong, right? It's not 45. Okay.
We did the second one on the.
Yeah. All right, guys, let's see. So just a quick little thing I'm noticing, if you're struggling with it, see this equation. The first one we did, the reason we picked the second equation and we isolated for y is because that y literally was by itself. Like the only thing that was next to it was plus 2x. So what I'm noticing is some of you guys, for example, on the second problem, you're trying to isolate that y, which is fine, you can do that. It's just, it's gonna make, if I start isolating this y, I'm gonna end up with nasty fractions. Okay, so maybe don't isolate that y and maybe don't work with the second equation, but instead try to isolate from the first equation.
Now, do you have to isolate y or can you isolate?
Nope, you can isolate y or x. So notice that this one's easier or simpler. So try to isolate one of the variables here. Would you rather isolate the y or isolate the x? Sure, okay, so let's go with this one. I'm gonna isolate, I'm gonna pick that one to isolate. So what do I have to do to isolate the x? Add y to the other side. So then you end up with that right there, right? The second equation, I'm just gonna rewrite it. And so here's what I'm saying, you guys get the freedom of picking the equation and picking the variable. So, you know, you just have to do more practice to kind of get that intuition. Okay, so for the first equation, we isolated for x. And then that means that whatever this x equals is gonna go into the x of the second equation. So then this becomes 7 times the expression that x equals above, plus 6y is equal to 5. Notice so far I don't have any nasty fractions. What do we do from here? Let's see. That's right, distribute the 7. So we get 70 plus 7y is equal to 6y. Oh, here's another mistake I've been noticing some folks doing. What do I do from here? Combine like terms. Okay, this is what I'm seeing some people do. Okay, so just be careful. You're doing this. You're subtracting the 7y, but then I think you're confusing combining like terms with moving one term to the other side. I would minus the 7y if I'm trying to bring the 7y to this side. So if I subtract the 7y, I have to do it to the other side of the equation. That's a different concept than combining like terms. For combining like terms, I don't have to do the opposite. Oops, careful. You don't have to do the opposite. You literally just get this positive 7 and add it with the positive 6, which gives me 13y. Yeah, there's no subtraction that I need to do here. And then let's see, what do we do from there? Get the 70. See now how I'm subtracting the 70 because I'm moving it to the other side. Whatever I do on one side, I have to do it to the other side. So I get 13y equals, what's that? Negative 65. Does that go 13 go into that?
Yeah.
Sweet. Oops. What did it give you? -5. So y equals -5. When you get this -5, you can plug it back into the isolated variable equation or the original equation. Maybe this one's easier. But then you're going to plug in the -5 into the isolated equation. So that's 10 plus -5, which is really just 10 minus 5. I give you 5. But okay. So we get x is 5. Oh yeah, be careful, be careful. You gotta make sure you label it. I saw some people putting -5, 5. X is 5 and y is -5. So that's my answer right there. So just I think the biggest thing right now is just knowing what to pick and what to isolate. That's what I'm noticing was the conceptual roadblock there. That's it for substitutions. It's kind of a little repetitive after that. Okay, but it's a lot of algebra that you guys will have to mess around with. Any questions? Okay, any questions you think someone else might have? Not necessarily your question. I mean, you guys, I'm training you guys to be tutors eventually. So I'm a tutor guy, so. Okay. So for this one, would you rather isolate this x, this y, this y, or this y? Sorry, this x or this y?
The X and Y. and-
This one?
Then subtract the x.
Yeah, and here they're both positive, right? So either the x or the y that you isolate will give you the solution. All right. All right, guys, next comes the other one, the elimination one. But before we jump into the elimination, I want to go back a little bit on that whole multiplying equation by a number real quick. Let me bring this down. All right, let me jump onto Desmos. Let me erase this. Okay. Give me a random linear equation. That's not in slope intercept. I had 3. Okay. So there's this line right here. Okay, let's color. Let's give it a color. Okay. Okay, so let's see. Let's multiply this equation by a random number.
4.
Multiply by 4. Okay. Let's see. So 4 times that equation. It's reading it as incorrect, but that's fine. What do we do with this 4 to do that? It's kind of like you're distributing it. Technically, what I should be doing is multiplying the left side by 4 and multiplying the right side by 4. That's what I really should be doing. Like that. So then that's going to give you 20x plus 8y equals 12. Probably. And so you guys see how we're getting the same exact same line? Okay. If I told you guys to turn this into y-intercept form, and I told you to turn this into y-intercept form, what can you conclude will happen? It's going to have to be the exact same slope-intercept equation because it gives you the same line. Okay. What if we multiplied it by -4? You think it'd do some kind of reflection thing? Let's see. So let's multiply by -4. So that would be what? -20x 8y equals 12. I should put times here. There we go. So notice again, we get the exact same line. Okay. So it doesn't matter what kind of number you multiply on both sides of the equation, you will always get the same equation back. It will represent the same thing. Is that okay? All right. If you multiply an equation by a number, what happens to the lines? Stays the same. Okay. So that conceptual piece is crucial for this next method here. I'll leave that here for a bit. Okay, so let's go back to that same old problem that we were messing around with. No, we're not. And so now we're going to do what is called the addition method, but it's also known as the elimination. All right, let's see. We're not gonna solve it right away. I'm gonna talk a little bit about the theory, okay? It's very weird, why it's true. But it's very useful. Okay. We already did this 3 times. Okay, what's the solution point? 2, -3. We already know that. Okay. So let me just add that here real quick. So we know 2, -3 is its solution point. But let's do what you guys did on the one. I'm going to substitute the x and y coordinate into the equation on the top. So that would be 2. What happens when you plug in the -3 here? It becomes 3. That's supposed to give you 5, which it does. And if I plug in the same point into the bottom equation, that's going to give me 2 times 2 plus -3, which is -3. And that's supposed to give me 1, which it does. Is that okay? Okay. So here's what this the algebra, or no, the conceptual piece comes in, is because this is in the solution point of the system. That means that if I add the numerical values on the right side of the equation, right? If I add these guys, what happens when I add these 2 numbers? What do I get? 6. The sum of these 2 numbers has to equal the sum of these 2, because technically this is the 5 and this is the 1. So let's see, 2 plus 4, 3 plus -3. And so notice that we get equality on both sides. But that only works because this is the solution point. Okay? If it wasn't the solution point, then now we're not here. So the idea behind this method is we're saying, okay, since we're looking for the solution point, that means that if I add both of the values of the equation on the right side, only the solution point will happen if, when I add the left-hand side, these 2, the left-hand side and the right-hand side, must stay equal. Okay? So now we're going to assume we don't know the solution point. And so for this method, I'm just going to rewrite the equations again. For this method to work, what you're going to do is you're going to add straight down. You're going to add the left-hand sides with the like terms and the right-hand side. And then you add straight down. Then you add. And then we get the x term with this x term gives you 3x, -y plus y, 0, 5 plus 1 is 6. And so notice we just get an equation with x. Right? That x has to be the x of the solution point. Let's see. Divide by 3, divide by 3, x equals 2. That 2 right there. Okay? So it's uncovering the solution coordinate because of the equality of the right-hand side and the left-hand. And so just as before, you found one of the coordinates. So then you just get that coordinate and you plug it into either of the equations. Probably do the one that's simpler. Which equation do you guys want to sub it into? The first one. So let's sub into the x minus y plus 5 equation. So then that's going to give you 2 minus y is equal to 5. Let's subtract the 2. You get -y equals 3. What do we do after that? Divide by -1. And then you get y equals -3, the solution. Yeah,
Is there a situation where negative variables will cancel out
there's that most likely.
or both?
What do you mean, will they both cancel?
Yeah.
Correct. Yeah, well, I'm gonna show you both all those pieces. So this method is usually considered faster because I don't have to substitute one variable into another equation. Instead, it's completely different. We add the left-hand side with the right-hand side with the hopes that one of the variables gets eliminated. So that now I get a new equation with just that one variable and solve for it. Solve for it, and then you substitute it just like you did earlier.
And then if both variables are still existing, it would be best to use the other method.
That's exactly what we're gonna do right now. So, I think that was your question too. So let's say you add straight down and it wasn't as convenient as this and the variable got eliminated. So then there's still a way you can use this method. Right, let's see how that's gonna work.
Yeah, it's gonna make it like separation really useful.
Yep. Okay, let's do some more examples here. Let's do example 2. So let's say we're asked to solve 3x minus 5y is equal to 1, and 7x minus 10y is equal to -6. And I want to use this addition method. So first, let's add straight down so you guys can see what these two folks were talking about. Let's say I want to add straight down. 3, what happens when I add the x's? 10x. What happens when you add the y's? And then I get what's that, -5? So what they were trying to say is, you guys see how in this case, one of the variables didn't just cancel off with itself? So you're still left with an equation with 2 variables. So you're that didn't really work to your advantage. So what you're gonna do, so this wouldn't work here. It's not gonna it's not gonna take you anywhere. So what you're gonna do is what we're just doing on Desmos. I'm gonna multiply one of the equations by a number to make it different so that when I add straight down, now a term will cancel. But because I multiplied by the equation by a number, the line's still the same, so the intersection will still be the same.
So we were talking about
Well, here's where yes, here's where you're gonna say which one's easier to eliminate. Is it easier to eliminate the x's or the y's? The y's, right? Because if I can just turn this coefficient into a +10, then it'll cancel with this -10. Perfect. That's exactly right. So that's how you're gonna start this method. You're gonna look, you're gonna add straight down, crap. Something doesn't they both, one term doesn't cancel. So then I get to choose which equation to multiply a number by. Okay. So you guys are saying, so let's multiply equation 1 by -2. So I'm gonna do -2 times 3x minus 5y, and then I'm going to multiply the 1 by -2. I'm going to do it to both sides. That's going to turn this equation into is equal to -2. See how it looks different? But on Desmos, it would be the same exact line. Okay. Now I get this new equation, and now I'm going to add it with the second equation. Okay. So now let's add this new equation with the second equation. Let's see what happens now. Now let's add this new result. -6x plus 7x, x. Here, boom, those cancel. -8, look at that, boom, we already got one of our coordinates. Okay? What do we do with that -8?
Plug it into I have a question. Can you plug it into the -6 return line?
Correct,
Or you can do it in this.
correct, or this one. Yeah, either one.
Even like, despite the fact that it cancels out, you can still.
You could still do it because remember the solution point,
Mhm.
if you plug in the coordinates, it's supposed to be satisfy all of these equations.
Okay.
Yeah. So maybe let's do it. Which one do you guys want to pick?
Just like that.
Top one? Okay, so let's sub this. So sub into 3x minus 5y equal to 1. We're replacing the x with -8, so that's 3 times -8 minus 5y is equal to 1. That's going to give you -24 minus 5y is equal to 1. Ooh. What do we do from there? 24. Then you get -5y is equal to, oh, nice, 25. And then divide that -5 off. And now we got y is equal to -5. So what's my answer? Correct. Oh, does that help? Did you get this question?
What if you want like the other way where neither or both of them will cancel?
We will, we want to, yeah.
Thank you for letting us choose which method we want on the test.
Totally, yeah. And then towards the end, I'm gonna show you when to know which method will be easier. Okay, I'm gonna have you guys earn your break. Okay? Let me have you guys do 2 of these and then we'll take a break. We'll solve using addition method. Or the addition method. Okay, let's see. So first system is gonna be 3x plus 4y is equal to 5. Second one is x minus 2y is equal to 5. And then the second equation, or the second system is -x plus 3y is equal to -7. X plus 3y is equal to -11. There's a lot to keep track of, so be careful and be organized with your algebra. Okay, because things are moving all over the place now. Maximum time that we do is very good. If I want this to add and return to that, I want this number to be positive. Because the other part is negative. I have a negative part, I just have to turn that into negative +10. I have to multiply by the -2. But as a result, I have to multiply the whole equation. Okay? That's exactly. Exactly, because eventually, when I have this problem. Remember, you get to pick the number that you want to multiply the equation by, okay? To work to your advantage. Eliminate the number there. So that's probably less than you're doing the addition method, not substitution. Yeah, I want you guys practice both. And then just FYI, both methods are used a lot in the calculus course. Both, not just one. Okay.
Seems like through five. It's like the five. Maybe one.
Oh, I thought you
Oh, I feel good.
You guys can check your work, your solution. Oh, darn it. I left. Shit.
Oh, is that negative? Oh, my bad. Seven.
All right, guys, let's take a break. I can stay answer questions. Come back at 2:10. We're almost done with this section. Okay, so far every system has been consistent because there's been a solution to every system. So I want to show you guys what happens with the weird scenario when it's inconsistent. So let's take a look at what's going to happen, right? How does that look like? So let's take a look at an inconsistent system. Or let's just say there's no solution. Let's see what that would look like. So we're told to solve 6x plus 7y is equal to -10. And then we got -6x minus 7y is equal to 8. So as I said before, on the exam, I'm not going to force you to choose a method. You can do substitution or you can do elimination. But here's my tip. Normally you want to do substitution if one of the equations just has a variable without a coefficient. Because then it's easy to isolate and you just move the other term to the other side. So if it was like this, I'd probably want to use substitution method and just isolate that y to make it simple. My life. Okay. But in the case where you don't see anything like that, most likely you want to do the addition method. Okay? So which method do you guys want to try?
Addition.
Addition. What happens? Do I have to multiply an equation by something? No. Which variable do you want to eliminate? Yeah, notice that when you eliminate here, you just get 0, 0 equals what? -2. So if all variables are completely gone during the algebra, what's happening is that it's saying that these two sides will never be equal. No matter what x coordinates and y coordinates you plug in, you will never get equality. That's another way of saying that there's never going to be a solution. The lines will never intersect. There will never be a point that satisfies it. So when you see the variables completely get eliminated, disappear, and then you get one number on one side and another completely different number on the other side, that's the algebra telling you that there's no solution. So what do the lines look like? They must be parallel. Okay. So no solution, I stop here. And so in this case, we get parallel lines. They must be parallel lines. Which you can then go, did I mess up somewhere? Right, on the homework, graph it, maybe you graph it using decimals, confirm, oh yeah, they are parallel. Okay. That's this extreme case. Questions? Yeah, big. Yeah, you're talking about this guy right here? Let me actually, before I answer it, let me see what WebAssign tells you to do. Let me see. Let me look at the directions real quick.
Usually we'll tell you, but if there is no solution, put no solution.
Okay.
If that's a possibility, usually let's flip it to the-
If it's on a test, just write no solution. Yeah, like write it in words. On WebAssign, it says if there is no solution, enter in all caps, no solution. Yeah, it says it right there. Okay. So now I want to show you a different example. This is an example when you have an infinite number of solutions. What does that mean? Let's see. So let's say it's solve 6x plus 7y is equal. Oops, sorry. I was writing from the original. This one here. Let's say it says x plus 2y is equal to 6. And then we got negative 2x minus 4y is equal to negative 2. This time, let's do a different method. Let's do the substitution. Which equation do we want to use, and which variable do we want to use? Isolate that all by itself. Let's isolate that. Let's do substitution. Let's use substitution. Okay. When I get x by itself, what do we get?
-2y plus 6.
That's right. You get that minus 2y because you subtracted 2y to both sides. Plus 6. And then I'm just going to bring down the second equation. Okay. So then we're going to substitute with x equals into the other x of the second equation. That's going to give me -2 times -2y plus 6 minus 4y equals 12. And then distribute the -2. Be careful here. That's 4, right? 4y minus 12 minus 4y is equal to -12. All right, let's see what happens.
0 equals 0.
Negative 4y.
They end up canceling out. So you get -12 equals -12. Okay. So it's kind of, notice the variables completely vanished from the equation. But we got, and unlike this one, here we get the exact same number on both sides. That's the algebra telling you, oh, there's an infinite number of solutions. Versus if this ended up happening, that would tell you
There's no solution.
there's no solution. Okay. But if you have the same number on both sides, this tells you that you're going to have an infinite number of solutions. So you'd say infinite number of solutions. Yes, question.
Does that mean that if the equations wouldn't be functions because they're like moving around and like crisscrossing multiple times?
That's a beautiful question. So are the graphs like crossing themselves in infinite? Like, are they doing this weird like little funky things? Well, the graphs they can't be curved because the graphs are lines. So notice this equation. If I multiply this equation by -2, it's the second equation.
Oh, okay.
So in reality, they're the same line. They're the same line. Okay. So when this happens in this case, you're getting the same line. Now, what WebAssign might do, actually, let me read it to you. What they might say is they'll say, they might say something like, oh yeah, it'll say, if there are an infinite number of solutions, enter a general solution in terms of y. And you're probably like, what the hell does that mean? Okay. Well, if I rewrite both of these equations in slope-intercept form, okay. So they're going to be the same line. So here's what they mean by the general solution in terms of what? This is what WebAssign says there. So if I get the first equation and I get it in slope-intercept form, minus x to both sides, you get 2y is equal to -x plus 6, and then divide by 2. So that's going to give me y equals -1/2 x plus 3, right? So both of these equations, both of these equations, 1, 2, 3, 4, 1, 2, 3, 4, are going to be the line that crosses at y equals 3, and then the slope says to go down 1 over 2. So both of these lines are that line. Okay, and this is what they mean by the general solution. If I pick a random point, this part's a little conceptual, okay? If I pick a random point on this line that has the x coordinate x, what will the y coordinate look like? That's a conceptual part. What do we do to that x? What would you do to this x coordinate to figure out the y coordinate? You include it here, right? That y is this. So this is what the general solution looks like. All points, infinite number of points, but all those infinite number of points will always look like this. Meaning whatever the x coordinate is, the y coordinate, you'll have to use this to compute the y coordinate. That's what they're saying. So
should just input some point on it.
no, you will literally have to input this point right here. That's what's called the general solution. Okay. It's a little conceptual. Yeah. There might be like 1 or 2 in there. Okay. So you can go back to that video. What the hell did you say about general solutions? It basically means they're the same line, right? Find the slope intercept form of them. And then the point is x comma that slope intercept form. Okay. That's it for the section. Okay. So on the next one, we're gonna go off of basically what we just did, but now we're gonna involve inequality, which gets a little, can be a little funky. Okay. But I want to start this section with an actual application, so that's not this boring grammar. Okay. Let's see. Well, that's kind of like a little warm up, but not really. Let's see how this is gonna work. We're gonna use it's a lot of the similar stuff that we just did. This part, I'll leave this here. This one, record that. All right. College math, man, we go so fast, sorry. Systems, sorry, solving systems of inequality. Solving systems of inequality. Let's play with a little warm up before we jump into it. All right. We're gonna use the famous example of creating a fence. Okay, or maybe if you're in art and you have to make a frame for your art piece, right? Something that involves perimeter of a rectangular shape. So let's say for the fence scenario, we have 100 feet of fencing. Okay, and we need to figure out, we're gonna create rectangular shapes here. What's one possible dimension of a rectangular fence I can make with, actually, let me write this down. So given 100 feet of fencing, let's explore possible dimensions of rectangular fencing. Very popular example that you guys will do in calculus in a section called optimization, which you guys are gonna hate. Maybe not, maybe you like it, okay? I wouldn't, maybe let me not just give it shade already, right?
Is this have anything to do with like length and width and height?
It'll be there, yep. Yep. Okay, so but I'm prepping you guys now, because I know where you're going, okay? So let's see, give me a possible fence that you can make with this. With 100 feet of fence. So 25 by 25. Oops. Yeah, and then 25 all around, but we'll just say this is 25 by 25. Okay, let's see, 25, 25, that's 50, then another 50, that's 100, right? Give me another one.
49, 49.
Oh, you want extreme, I like it. Okay. So you're saying 49, 1. 49, 1, okay? What's the let's see, what's the perimeter of this rectangular fence? Meaning you're adding the lengths of all the sides. I know I'm speaking geometry words here. You're like, okay. Perimeter. What's the perimeter of this fence here? 100 feet. You're adding 25, 25, 25. What's the perimeter? I'm just gonna call it P here. 100, okay. Give me one where it's not 100, but that's possible to make.
So you're saying like leave some fencing, like
You can leave some fencing.
420s.
Huh? 20? Or 20s? Or 20s, you so nasty. Sorry. 20 and 20. Okay. So what's the perimeter in this case? 20 plus 20 plus 20 plus 20. It's 80. So that's fine. You can do that. Okay. Give me a fence that you cannot make.
1 and 2.
What?
1 and 2.
Like 1 and 2?
100, 200.
You could still do 1 and 2.
275.2 on every side.
This one would be perimeter. Hold on. What's the perimeter of this baby one? 6, but that you still have enough fencing for that. That one's still fine. So this is feet. Feet. Okay, so give me one that you cannot make. What? 69 and 200? All right.
20.
I'll do 20. All right, help me out here, what's the perimeter? Let's see. 90, 180, 78.
40, 60.
Well, let's see, 70 plus 20 is 90. So that would be 90 plus 90 is 180.
No, I didn't remember.
Minus 1, minus 1.
78?
78. Okay. Can we do that, Vince?
No.
No, why not?
These are amount of fence.
We don't have that much fencing. Okay, so that one is too big. There we go, that's the end of the session. Just kidding. And that's kind of what's happening, okay? Now, unlike what we were doing before, we're gonna think of the X, you can think of the X as like one dimension and the Y as the other dimension. Okay? And in this case, we're gonna explore what are all the possible X's and Y's that will satisfy our inequality. But notice there are many different answers, and there's some that just don't work. Okay? So that's kind of where we're going. So hopefully the visual representation kind of helps out. And so here's a good example of what's called modeling, where we have like a non-mathy sound, like not too hardcore mathy question, but we're going to use math objects to represent it and then use the math to answer it. Okay, let's take a look. So let's restart and let's consider a rectangular fence with length y feet and width x feet that uses uses up to 100 feet of fencing. So again, it's weird. Okay. So in this case, we're going to draw a shape to help us understand what's happening. Okay, so let's say this is the width and this is the length. Okay, so if this is the width, what are we going to label this? X. This is the width. Sorry, length.
Y.
Y. Okay. I know, a little bit of geometry. Okay. So if I have a rectangular shape with these dimensions, how would you find the perimeter? It'd be x plus x. Okay, you guys are doing x plus x. X plus x plus y plus y, right? Like essentially that's how it's happening. But because these two are the same and these two are the same, what's x plus x? 2x, not x squared. I heard somebody say 2x squared. Be careful. And 2y.
We could do 2 times x plus 1.
2 times, yeah, you can do that too. So this here represents the perimeter. We're using an equation. We created our own equation to tell us what it's representing. Okay, and so here's where the inequality comes in. What do we know about the perimeter if I can use up to 100 feet of fencing?
It'll be less or less to or equal 100.
The perimeter can be, what's the biggest it can be? 100, right? So P has to be less than or equal to 100 feet But what is the formula that we're using for P? This tells you that 2x plus 2y must be less than or equal to 100 feet of fence. Okay. So then what we're gonna do is we're gonna use this inequality with now two variables. And you can think of it as what we were doing here. Notice if I plug in 25 in for x and 25 in for y, does it satisfy the inequality?
Yes.
Yep. If I plug in 1 and 2? Yes, but if you plug in 69 and 20, it will not satisfy this inequality. Okay? But what we want to do is we want to solve this inequality, meaning what are all the possible x and y's? That's hella x's and y's. Okay? So what we're going to do is we're going to graph a two variable inequality and kind of see where that takes us. Yeah,
To clarify, anything with like a greater than or less than, that's referred to as an inequality.
correct. Yeah, anything with these symbols. Yeah. So to understand all possible x and y dimensions, we graph the equation first. You're going to start by graphing the equation of the inequality. 2x plus 2y equals 100. Okay, so let's see. 2x plus, or let me just do this right here. Like that, x, y. Again, you're not going to do all this on the homework. This is more of the theory building up to what we're doing. Okay, if I asked you guys to graph this, well, what is it that you would want to do to this equation first?
Put it in slope.
Put it in slope-intercept form. So you probably want to do that first. So let's put it in slope-intercept form. So let's minus the 2x to this both sides. We get 2y equals minus 2x plus 100. And then divide everything by 2. So then you get y equals negative 1x plus 50. And so where does the line cross the y-axis? At 50. So let's go in increments of 10. 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. And 30, 40, 50. Okay, so we know the line crosses right here. What does the slope tell me I do?
Down one.
It goes down 1. You're right. It does go down 1 over 1. But because we're using increments of 10,
Down 10 over 10.
it's notice that this is equal to negative 10 divided by 10. They're both still negative 1, right? So I'm going to go down 10 over 10. Down 10 over 10. Down 10 over 10. Down over 10. Down 10 over 10. Down 10 over 10, right there. And so that's going to be this line right here. It's going to be crooked. I apologize, but that's that line right there. Okay. So let's see. This guy right here, this dimension of this square, what's x and what's y? 25, 25, which would be right 25 by 25. That's going to be right on here, around right there. So that's 25, 25. Is it on the line? Yes, because the perimeter is exactly 100. Okay, question, go ahead.
So everything inside the line and on the line is feasible, while everything outside.
What's your inside? Is this the inside or is this the inside? So you're saying on this side, yeah. So anything on this side you're saying is feasible, anything on the other side is not.
Well, as long as both are positive, though.
A little bit, yeah. So this dimension here was 49, 1, right? So it'd be 49, 1. That's gonna be like right there. Then you guys gave me this one. 20, 20. So that's 20, 20. That's right here. And then you guys gave me 1, 2. 1, 2, that's like right here. So yes, noticing all the feasible ones seem to be below the line. And then there was this one, 69, 20, which is like somewhere over here and then here. Here was 69, 20. So that's correct. And then Bobby's question was, well, because we're thinking of dimensions as like distance of a fence, we don't want X and Y's to be negative. So if you guys put everything you just said together, that means any point that lies underneath the line in this region here is possible for your fence. Any point with any rectangle with the X and Y coordinates here will work. Okay. I think I went over this in class, but what's the name for this fourth of the, like, what's the name of this section? First quadrant. I forgot to mention that when we were learning all this stuff, but this is called the first quadrant, second quadrant, third, and then fourth. That's gonna be important for trig later, okay? Yes, question.
Leftover for something you're supposed to write.
Well, we're not done. We're not done right now. So the answers to these, the graphs to an inequality are regions. So this is the graph of this inequality, is a region. And so they usually call it a shaded region. Okay. So let's just look at a completely different inequality and let's try to graph its region. Try to graph its region. But here I'm not going to give it any like context with like application. I'm gonna have you guys try some. All right, let's see. So it'll say graph the inequality X minus Y is less than 5. So for all these, what you're going to want to do is you're going to start by graphing the equation associated to the inequality. So you want to start by graphing its corresponding equation. X minus Y is equal to 5. What do you do to that equation to start graphing it? So turn it into slope intercept. Minus the X. Divide by -1. Then you get Y equals X minus 5. Okay, that you use that equation to help you figure out the boundary of your region. A lot of graphing, I apologize. Let's see, 1, 2, 3, 4, 5, 5, 1, 2, 3, 4, 5. Okay, where is my y-intercept at? That's -5, that's my b value. And my slope is 1. So that's my slope right here. But I'm thinking of it as 1/1. Okay, so I'm gonna go 1 over, 1 up, 1 over, 1 up, 1 over, 1 up, 1 over, 1 up, so on. Here's where you gotta be careful when you graph it. When I graphed this inequality, you see how it has an equal sign underneath? because it was okay for the perimeter to equal 100. Okay, but if there was no equality here, then I do not want the perimeter to be 100. So in that case, what you do is you still draw the line, but it has to be a dashed line. It has to be a dashed line to say this is the boundary of my region. I just do not include my region. It's kind of like when you guys were doing intervals, you had an open circle or a closed circle. It's kind of like that. So when I sketch my line here, is it a dashed line or is it a solid line? Dash. So this part here tells you
It's solid when it does include numbers.
it's solid when there's an equal sign underneath.
Yeah.
Yeah,
The
Yeah.
brackets,
Yes.
Oh, you're thinking like intervals? Yeah.
Yeah.
Yeah. So here, because there's no equal sign, so no equality tells you that you're gonna have a dashed line. So you're gonna have to make a dash. Just seeing something here. Okay. Okay, so now the question is, which region do I shade? Do I shade above the line or do I shade below it? Okay. It could be a little confusing for some. Here it kind of makes sense because of perimeter, right? But in this case, there's no context to it. So, one easy way to check,
where the arrows pointing, right? Of the inequality.
there's several ways to do it. Okay. Out of the multiple ways I've tried, the one that I felt has helped the most is asking yourself, does my region include the origin or does it not include the origin? Let me show you what I mean. So, where do I shade? So then you want to see if check to see if the region includes the origin 0, 0, because 0 is just a nice number to plug in. So what you do is you plug in 0, 0 into the inequality. Okay. I plug in 0 for x, plug in 0 for y, and then I check if this inequality is true. What's 0 minus 0? Is 0 less than 5?
Yes.
Yes. So then I include the region that includes the origin. So then I shade so that I include the origin above like this. Okay. If this was false, then don't include the region and then shade away from the origin. Yeah. And so the graph of this inequality is the region shaded and the dashed boundary. All of that is part of the graph. Oh, yeah.
Would you think of it as reading it left to right, and you would do it that way?
Yes, if it helps, however, it's helping you. Yeah, like some people see, oh, this is less than. The only thing that might be tricky is because sometimes it's negative flips the inequality. And that's where it gets like a little bit scary. But this one will for sure, you just plug it in and it'll for sure give you. Can I have you guys trying to graph two? Okay, I'm gonna give you guys two. All right, let me have you guys for these. So, graph the inequalities. Okay, number one is y is less than negative 2/3 x plus 4. I already gave it to you in slope intercept form. And then number two, I don't give it to you in slope intercept form. Notice this one does not have inequality. This one does have inequality. Underneath. Okay, just be careful. Yeah, let's do that. I want to see something real quick. There you go. There you go. Perfect. I'm gonna give a chance to check with your classmates. Remember, this is the y-intercept. That's your slope. Luna? So this is right there, okay. It's just your older question from last one.
Reading off of that, I just kind of did zero.
Go two, and then when you go 3, 1, 2.
The run, I just say up and down.
So maybe 3, then go 2. Then the practice to grab -2 with this guy. So would you just grab
You would go down to the y-axis.
2 and then run 2? When you go left, that's what I meant about running.
Yeah,
Okay.
right.
So -2 is -2, you go down to 2 and then go right. And then the y would be 4.
The shape of.
Like,
In terms of.
you know how it's 4 right there? So that's the y.
Oh,
Yeah. And then you just. You have to, like, I've been thinking, like, do I have to solve?
Just continue.
and you really need to solve this where. Yeah.
Okay.
Sorry,
Okay.
I think even thinking is the nation kind of acting like.
Yeah. Okay, let's go.
Well, I'm going to go.
And since it's. That's a lesson. Where to go? The shade will look this way. That's what I'm trying to fix. So that it's raining.
Zeros and X and Y. That's the, if that equals one. So 0 and 4. So then that point, we just correct 0, 0. And then so then that is true.
So that's. That makes sense.
For this problems, yeah. Down to.
Or do you plug it? Okay.
Let's see. 7. All right, guys, you guys can check your work here. So both of the regions will include the origin. If I plug in 0, 0 here, I get 0 minus 0. It's true that 0 is less than 7. Okay. So hopefully your regions look like this. Here we do not have equality, so it's dashed. Here we do have equality, so you do include the line. Okay. Let me show you. It's a little funky on WebAssign. So let me show you. How am I going to do this on WebAssign? So let's see. That way it's on the video. You guys need to reference it. So here's an example question. I'm not going to solve it, but I'm just going to show you. Okay, so notice it gave me this inequality right here. I'm just going to just show you the tools. So if I want to draw a line, I go here, I pick the line feature. I pick a point, so maybe like my y-intercept, whatever it is. And then I just pick another point. The slope tells me the next point is here. So you see how I drew a line for me? Okay. But here's where, let's say I wanted to make it dashed. I don't want to make it dashed because there's an equal, but let's say I do want to make it dashed. From here, once you draw your line, you click the line button right here. And then it says dashed right there. So then you click that. Okay. Once I do that, now I want to decide, do I include the origin or do I not include the origin? Let's say I do not include the origin. So then you click the fill button. And then you click the little paint bucket on that region. And that's what you submit. That would be the answer. Right? And that's how I would submit the answer. Cool? Okay. We're not done. There's still more. We're not your, it's basically what you just did, but one problem. Let me show you what I mean. So what we did is we basically, this is the solution region of this inequality, and this is the solution region of this inequality. So now we got to deal with a system of inequalities, which means I'm dealing with more than one inequality at a time. Okay. So we're gonna use what we just did to do systems of inequalities. But it's pretty much the exact same thing you just did, with a little bit of a twist to it. So to solve a system of inequalities, we need to find you can think of it as intersecting, or you can think of it as the common shaded region that satisfies all inequalities. So to solve a system, you're gonna get one inequality. It has its own shaded region. And the other inequality has its other shaded region. You're gonna see where they overlap. Okay. But you're gonna graph them right on top of each other. So it'll look something like this. It'll say solve. Let's say I put this inequality. Y is less than negative 2/3 x plus 4. And then I have this inequality. 3x minus y is less than or equal to 7. The way you solve this is you basically do what you just did, but on top of each other. Okay, what do I mean by that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. Okay. You start by graphing this inequality, and literally, what you got here is your answer. So that was what the y-intercept was. 4, 1, 2, 3, 4. And the slope told you to go down to over 1, 2, 3. And what kind of line is it? Let's call this, let's name it so you guys can see it. So let's say this is inequality 1, this is inequality 2. So inequality 1, the line is dashed because there's no equality. It's a solid line, correct. And which way were we shading?
This side.
Below, right?
Yeah.
Includes the origin. That includes the origin. Because if I plug in 0 for y and 0 for x, I end up with 0 is less than 4, which is correct. So it includes the origin below.
How do you know if we only have to see the text? Like, I don't.
If so, like, yeah, like let's say you do all this here and you get you ended up with negative.
Then you have to.
0 is not less than negative 4, so it does not include the origin. It should shade away from it.
Okay.
Correct. All right, this guy here, let's see. When you guys got this and when you isolated y, I believe you guys got 3x minus 7. Just kidding, greater than or equal to. When you isolated it, yeah. Okay, so then here you would go, let me do it in yellow or in green. Y-intercept is 1, 2, 3, 4, 5, 6, 7. Slope is 1, 2, 3 over 1. What kind of line is it? Solid. It's solid. Yes. And we shaded,
To the left.
it included the origin, so you shade towards the left. So what's the answer? The region that where they overlap. So it's this part right here. It's this guy right here. It's a little annoying to draw, okay? Oh. And the line is solid here, but it's dashed here. Okay? So it's basically you're doing two of these at the same time. That's pretty much what happens. Okay? This concept is used for usually like industries that are trying to optimize revenue or what's the least amount of time that my process that I need to use my whatever machines to save me money. So anything that has to do with optimization, there's equations involved that model the behavior of those things. And then it turns out that intersection points of these regions turn out to be the optimal situations. Okay, we're not gonna have to do that, but I'm just showing you where this is used. You might have to do that if you take higher level math. Okay, and now. Okay. But that's it for this section. I know, it was a lot.
Let's see, I will one. Solid line.
Because it has an equal sign, that's why
And
it's
it
solid.
doesn't,
Yeah, correct.
just think of a line on the bottom, solid.
All right, guys, good job. Oh, dang it, I keep sharing my screen.